Awesome. Okay, quick review of torque, just so everybody makes sure that we remember everything that's important when it comes to torque. Torque is a quantity that measures the ability of an object to force to rotate an object around some axes. The classic thing that we talk about most of the time is a doorknob, like the doorknob that we have over there. You'll notice that when you push on a door or a doorknob, and think about it, even just the door in general. Funny, we talk about the doorknob, but if we open a door, where's the knob on a door? It's right here, right? It's not in the middle. It's on the very end, right? It's always it's far away from the swivel. This is your swivel point. Why is that? Well, what we're doing is we're applying a force to cause it to rotate open. You with me? And we want to do that as far away from what we call the fulcrum or the axis of rotation as possible. We do the same thing with the knob, with the doorknob. We rotate it as far away from possible. And that's all based off of torque's formula, which is torque is equal to FD sine theta. Now, sine theta is really, they're talking about where you apply the force. If I apply the force at any angle that is not 90 degrees, then we would take sine theta, because if you look real quick, the y component, or the component perpendicular to the knob, the thing that's causing a rotation, that's the one. And so if you look at it, that would be the sine theta, because it would be the opposite. But most of the time, we apply a force directly 90 degrees. Well, what is the sine of 90? 1. So really, this formula, if you apply a force at 90 degrees, just becomes F times D, right? And let's talk about what these are. Well, the force is the force that's applied to the doorknob or the door, right, to open it up. And D is the distance from the axis of rotation to where the force is applied, okay? And so this is basically the idea of a lever, a simple machine. You create a mechanical advantage by applying a force further away from the axis of rotation, okay? So that's torque. So this thing we call lever arm is important. It's how far from the axis of rotation we apply the force, okay? And we talked a little bit about the formula already. If we look at this, force is in newtons, D is in meters. So your units are a Newton meter, okay? So if we look, but before, because sine theta doesn't have any units, but before we called a Newton meter a joule. In torque, we don't. We just leave it as a Newton meter, okay? Forces in meters, newtons, we said, distances in meters, and thetas in degrees. We talked about sort of applying the force at any angle, but the last little part that's important is sometimes you'll have more than one torque, okay? For example, and this is my terrible drawing you guys laughed at so much, okay? But if you look real quick right here, we've got a squirrel on a branch and we've got a bird on a branch. Both of them are applying a force downward called the force due to gravity, right? And that's because their weight is essentially pushing down on the branch. But both of their weights cause a rotation. Go back, please. Okay. Both of these cause a rotation. If you look, both of these will cause a rotation that's clockwise, right? Okay, so both are causing rotation in the same direction. So we're going to actually, if we're doing a formula for this, what we're actually going to do is we're going to actually do a formula where we're adding the torques together, okay? And remember, each torque is equal to FD sine theta. In this case, if we're dealing with the weight of an object acting on a horizontal thing, the sine theta is going to be 90 degrees. So we're just going to make that go away because it's times 1. So we do it's sine theta is 90 degrees. So we got to go ahead, and we've got torque, we're adding the torques in each of those forces because their weights is Fg, and we know Fg is equal to mg. So we end up with really the formula mgd plus mgd. Now that's not always going to be the case, but for this case it is going to be the case, okay? So we're adding the torques together. Now if two masses are on either side of the axis of rotation, we call this the fulcrum right here. These are two people that are on a teeter-totter, and one is causing a rotation like this one is, and one's causing a rotation like this. They're actually fighting against each other. And remember, kind of direction of clockwise or counterclockwise matters. So in this case, we would do torque 1, which is Jadeveon Clowney in this case, minus torque 2, which is my torque. And he would win out because he weighs a little bit more, okay? And we would figure out what is the net torque. How much rotation is actually caused. Rotations actually, net torques cause what we call angular accelerations. You don't really need to know that, but essentially what it means is it's going to speed it up moving in the circle, okay? So in this case, it would just MGD. All these notes are online, so you can look them up if you want to look at them, okay? We've kind of already talked about it today. But here's what I want you to do today, is what we're going to do is we're going to grab one of these guys, okay? And each one of these guys, I've got 2 masses hanging on them, okay? So if we think about this, this would be a net torque situation because we have more than one torque, right? So if I put a mass here, you'll see that this torque causes more torque than that. Now let's put this one here. You'll see that in this situation, we've got a little bit less. And if I move this one in, you've got a situation where maybe they just, there's a little bit of torque, right? And in this case, we've actually got a situation where this one causes more torque. Even though there's less mass here, this one causes more torque. Well, why would this one cause more torque even though there's less mass? It's further away from the axis of rotation, right? So it's a mechanical advantage, right? This is the idea of a lever, okay? So you're creating a mechanical advantage. Well, the lab I want you to do today is this. I'm going to place the big mass, and there's 2 masses. You'll have 2 masses. I'm going to place the big mass there, and I'm going to place the other mass here. Now, what I want to know is, can you figure out how much mass needs to go here in order to cancel out these 2 torques? So what we're going to do is we're going to do torque 1 plus torque 2, but what would I do with this one? Minus torque 3. Are you following me? Right? This would be torque 1 plus torque 2 because they're positive torques. This is going to create a negative torque minus torque 3. What is the net torque we want to get to if we want it to be horizontal? We want 0 net torque, right? So we need to set up a net torque situation, set net torque to 0, and figure out what mass M needs to go here in order to cancel out these 2 torques. Do you think you can handle that? Okay, so let's go ahead and do that, and we will see how it goes. All right.